Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe a few more concepts related to correlations. Now that we have covered null hypothesis significance testing for correlations, I want to stress this important point. It has to do with the interpretation of a correlation. Correlations do not equal causality. Even if the correlation is really, really large, that tells us nothing about causality. Why? Well, there are many reasons. First of all, we don't know what the true situation is, whether X would cause Y or whether Y would cause X. This is because we only have information about the relation between the variables, not whether one is truly predicting the other. Another situation that could exist is that there could be a third variable, we'll call it Z, that explains or causes both X and Y. A variable that explains or causes both X and Y is known as a confounder. Remember the ice cream example from earlier in the semester. Every year, increasing ice cream sales are related to increased shark attacks. The confounding variable is temperature, because hotter weather means more people at the beach and higher ice cream sales. When a third variable is present, Z, that causes or is associated with X and Y, then X and Y may appear to be related when Z isn't controlled, even when they are not associated in reality. In the ice cream example, summer is Z, the third variable or confounder. That is temperature. X would be ice cream sales, and Y would be shark attacks. Another example would be that neurotransmitter functions cause both feelings of depression and feelings of loneliness. The neurotransmitter function is Z, the third variable or confounder. X is loneliness, and Y is depression. Now let's turn to measures of correlation as effect sizes. Part of the reason people like to see effect size measures is that effect size measures tell you about the size of a difference or a relationship in units that are standardized. If you recall the definitional formula of the correlation coefficient, you'll remember that correlations are already standardized. They are not in original units of X and Y variables. They're computed using z-scores of X and Y, which are already in standard deviation units. A scientist named Cohen made some recommendations for interpretation in 1988, and they have become our standard benchmarks for small, medium, and large effects. A small effect is equal to a correlation of 0.1, a medium effect to a correlation of 0.3, and a large effect is a correlation of 0.5. Note that these differ from the benchmarks used for other effect size measures. Finally, I want to introduce you to some other types of correlations. Thus far, we have only talked about the Pearson product moment correlation, which is for two continuous variables. There are a few other types of correlations that might be relevant, especially to your course project. One of them is a point biserial correlation. This is a correlation between one continuous variable and one binary variable. A tetrachoric correlation is a correlation between two binary variables. These correlations should be analogous to the Pearson correlation if computed correctly. They make different distributional assumptions about the observed variables, so we're not assuming that the variables are continuous and normally distributed, as we are with a Pearson correlation. Lastly, we could examine a polychoric correlation, which is a correlation between two ordinal, rank-ordered variables. This concludes the 5th lecture on correlations. In the next lecture, we'll learn about linear regression models.